So Matei has huge contribution to systems in general and open source over the past 10 years. He started with Mesos. It was one of the main contributors and creators of Mesos, and then he created Spark. Then after graduating, he also had a bunch of very influential softwares, systems he developed like Weld, and more recently MLflow, which is used, which evolves, it's evolving as a de facto standard for tracking experiments in machine learning. And other than that, he was very prolific, publishing a lot of influential work at the intersection between machine learning and systems. Anyway, I think I took too long. So without further ado, please welcome Matei virtually.
Okay, no worries. Yeah, thanks, Jan. Thanks everyone for showing up. And definitely wouldn't be Berkeley without, random people like screaming around and making noise and stuff during the talk. So I'm going to talk here about building large-scale cloud software, primarily from the Databricks perspective, but I think this is a pretty interesting topic for research, and there's not that much research on this yet because not a lot of people get to build it, but it's sort of the main way pretty much all new software gets delivered today. So that's the perspective here. This is actually based on a keynote talk that I gave at SOCC, and I've modified it and extended it a bunch, but it's also a topic I'm interested in from a research perspective. And this talk is about what we learned in the process of building software at Databricks. It's got especially a bunch of contributions from the people here, but of course, most of the engineers at the company are involved in a lot of these problems and challenges. So as background, I'm going to start about why, look at cloud computing in general and what's different in developing cloud software from the traditional kind of on-premise software, the stuff you'd learn about in most courses in a university, for example. Then I'll talk about Databricks and specifically its product and challenges. Then I'll also talk about some of the challenges and solutions and research questions that come out of this. And throughout the talk, I think you folks, you can coordinate either using the chat or by just messaging Sammy to ask questions. And I also have time for questions at the end. So let me know if those come up. I believe I can make the chat visible somehow for myself. Yeah, and I think you can see it. So there it is. Okay, great. So let's start with this, what is the cloud about? So traditionally, when people were developing software, whether this is something like Oracle database or, Windows or whatever it is, the traditional way to build this kind of enterprise software was packaged software. So there's a developer team that works on it, and they make releases, and then the customers or users have to install these releases. And it's a lot of effort to ship a new release and get people to install it. So usually you would spend, 6 months to a year between each release, and then you would ship it out. You would test it. You'd say, okay, it's ready to go, and ship it out. And then after that, it actually takes time once you put these bits out for the customers and users to deploy it. So it might take another 6 to 12 months for them to upgrade their stuff and get it running for them. And each customer would operate its own instance of the software. And so they have both users and an operations team that runs it. So that's the traditional model. It's nice because you just focus on building the software and shipping it. On the other hand, cloud software works in a very different way. The whole point is that the developer will also operate it for you. So you've got this team that's both developers and operations. Often it's just an engineering team that does both. And you can actually ship stuff now much more frequently. Let's say you ship it every 1 or 2 weeks. At Databricks, we actually do every 2 weeks for most things. Other things is whenever we have an update, we actually just ship it. And this is deployed and managed by the vendor themselves, and then the users just connect to it through a web browser or API or whatever, and they can use it. So the result is that users are, always seeing the latest version of the software. They get the updates very quickly, and they also need less operational burden. They still have some operators because there's still a lot of things to manage with, who can use it, what can they do with it, how do you configure it, and all that. But it's just fewer, and also more people who would not have had the resources to stand up an internal deployment and an internal ops team can just sign up for a cloud service and begin using it. So it's actually, many times more people who even use your software to begin with if you offer it this way. So as a user, why would you want to use this type of cloud software? So there are basically three reasons and that people might do it. So the first is that you actually get the management packaged with it. So you're actually getting more value. It's basically a better product than just the software bits alone because it kind of runs itself. So that's extremely valuable. Actually, that's one of the main reasons people do it. And when we were starting Databricks, we had this debate and among the founders about how to build stuff, and Jan in particular pushed for let's just do cloud first because we think it will be the most popular way. People will want this in a few years when we're done building it, and that turned out to be true. So that's a big reason. Second reason, especially for this kind of data analytics stuff we do, is elasticity. You can pay as you go. You can scale up and down on demand. And so you don't need to think upfront about how to provision something. And if your workload changes, if you want to scale down or scale up, you can actually do that. It's very important, especially in the past few months, as pretty much every enterprise workload has to change in some respect. And then the final thing is just that you get better features released faster because of this way that things are deployed. So just imagine that I told you today you can get a product from 2 years into the future today. Would you want it? Sounds pretty awesome. So that's basically what's happening for these users who otherwise would have had to wait for these long release and deployment cycles. So that's why a user may want to use it. On the other hand, for the teams building it, it is more challenging to build in general. There are also some benefits to building it this way. So the benefits, first of all, the fast release cycle is great if you're iterating on your product and just trying to get feedback. It's also nice that you only need to maintain 2 software versions, the current deployed one and the new one that you're holding out, because all your users are on the same version. And there are also fewer configurations. So with the traditional model, you often got into this really nasty situation where there were 5 or 6 different versions in use at different customers. Some are more important than others, and you have to support all of them, and you spend all your engineering time doing that. But on the other hand, there are also some challenges, and perhaps the biggest challenge if you really want to take advantage of this agility to deploy stuff is how to upgrade without regressions. It's really hard to do this. It's not something that you normally had to do in traditional software because people would roll it out bit by bit and just not move to it if it breaks something. But it's really critical for users to trust your cloud. And you have to get very good at this and to be able to do it really quickly. When you put out a new version, how do you make sure it won't break stuff? And there are a lot of potential types of regressions to think about. There's API, like how do you not break it? You can't ask people to spend 6 months to upgrade, to your new API. There's semantics. There's also performance, scalability, many different things that fall into this. And then other challenges, building a multi-tenant service. So now you are hosting this for everyone. That creates scaling, security, and performance isolation problems that you wouldn't need to do if everyone had their own instance of the software. So that's a challenge I'll talk about. Of course, operating the service, all these things that that are providing value, like the fact that you manage it to keep it highly available and secure, and so on. So now you're doing this extra work, but on the other hand, customers would have had to do it themselves before. So it might have been even harder for them without a cloud service. And then one of the nice things is you can see in real time pretty much what's happening in the product and use that to improve its quality. So these are some of the high-level differences. I would focus especially on the upgrades and on the multi-tenant service thing. And I think upgrades is one that I see virtually like no research about, even though it's so critical. So my point is many of these challenges are not studied in research, and yet this is like the way that people are delivering software now. Pretty much no one's doing the old way anymore. So it seems like we should be paying attention to them. So about Databricks specifically, so I'll talk about how we saw these in our company. So I think people probably know about it. Databricks started in 2013 out of UC Berkeley, the Apache Spark team. We're actually operating at a very large scale now, larger than many of the cloud providers' own big data and machine learning services. So we run over AWS and Azure. There are over 5,000 customers. And we launch and manage millions of VMs per day that are processing exabytes of data per day. So that's actually quite a bit higher than many of the cloud services you hear about. And there are hundreds of thousands of users. And we have about 1,300 employees, 200 engineers. Last year, we said we crossed about 200 million in ARR. So it's a pretty small team, actually, given the scale. It's like tens of thousands of VMs per engineer, for example, that we have to manage reliably. To give you a sense of like how this kind of service goes, this plot here shows how many VMs we've been managing per day over time. So you can see it's continued to go pretty quickly, actually, even into 2020. So even last year, it grew by about a factor of 3 in 2019. And before that, it also grew by a factor of 3 in the previous year. So it might look like we weren't really doing anything until a couple years ago, but of course even the scale a few years ago was pretty significant. And the hard thing is of course getting the initial customers and showing value to them and so on. But after that, one of the nice benefits of the cloud model is this elasticity where if something is successful, people will keep using it over time. So there's both people adding new workloads and there's existing workloads getting more data coming in every day. And so this leads to this sort of increase in growth. And of course, we want to isolate users and protect them from having to deal with all the challenges of scaling. So our job is to keep up with this very fast scaling while being able to build the product reliably and add new features. Okay. This is a marketing slide with some of the customers. I'm not going to talk too much about them, but the main thing that's interesting is that there are a lot of what you would consider more traditional enterprises, not just tech companies that are running workloads on Databricks using Spark and Python and SQL and other technologies that we have available there. So actually some of the largest use cases are not the tech companies or the web startups or whatever that you'd expect. So just as some examples, so in biotech, there's a huge amount of use of basically genomics and proteomics and other automatically measured data that's now going into drug development and design. So Regeneron's an example of a company that talked publicly about it, but there are many others that do the same thing. A really interesting use case is in finance and regulation. So FINRA is the US regulator that looks at all trades in the in the public markets in the US and tries to identify fraud, insider trading, anything suspicious. They have over 30 petabytes of data, and they have these analysts using SQL and Python that are doing this analytics on it to find these patterns. And then another example is large-scale simulations and inventory management at Shell. So anything that helps them figure out, which equipment is likely to break soon or how to move stuff between different processing plants can provide a significant savings for them. And so these are some of the things that actually create large load on the system. It's not just people aggregating events from web applications. And these things with, automatically generated data like gene sequencing and IoT obviously provide a much higher data volume than any kind of data about individuals. Okay, so how does our product actually work, and like how does it get deployed? So this is another maybe interesting thing about how to build a product in the cloud. So we've got users, of course. We target you know, different individuals that work with data, and we've got a service that we manage. So this is all virtual machines that we provide with a bunch of APIs and user interfaces, a whole bunch of like policies and stuff. But then we also have to actually run the workload. And what we chose to do at the beginning is to run the workload in the customer's cloud account. So imagine you're a customer, you know, one of these large customers that already has some kind of agreement with AWS or with Azure. Maybe you've got a discount, maybe you've got some reserved instances. Also, maybe you've got an internal process for managing your virtual VMs. You've got an admin, you know, sort of like the John Kuroda who is trying to figure out how to allocate the resources. The nice thing about this approach, oh, let me see. Yeah, 1 sec, I just gotta check because there's some kind of smoke thing going on. I'll be right back. Oh, I guess it stopped. Okay. Probably something nearby. So anyway, so the thing, what we chose to do is to actually just get an IAM hole so that we can launch compute clusters in the customer's account and launch storage in it as well. And so this works well with everything they have set up, whether it's a financial agreement or some way they do administration. We just launch VMs in their account. We do install something on it, which is Databricks runtime, which actually runs the workload, but then it's running in their account. Now, there are also services that will do the compute themselves. We chose not to do that initially, but it might make sense to do in the future. But for at least large users who want to manage their cloud themselves, this is one thing that you can do. And the nice thing is also from a billing and financial perspective, you know, they get one bill from Amazon and one bill from us. We get very high margin. We don't think we're any risk of a customer using something and then not paying us for the compute and then us having to pay Amazon. So there's also some benefits in terms of like cash flow and the way you set up the finances to doing it this way. And then in our servers, we based everything on open source. So there's a lot of talk about like, you know, if you do something open source, can cloud vendors just replicate it and so on? And so we started with an open source project, of course, Spark. We support the open source data ecosystem. Most of our, you know, machine learning work, for example, is in libraries like scikit-learn and TensorFlow and PyTorch, and we're trying to run those at scale as well. And we even launched new open source projects, Delta Lake and MLflow. And the reason why we chose to do things this way is because the hard stuff is all the stuff I talked about with running a high quality cloud service and actually, you know, delivering the reliability, the availability and so on of that. So we want to focus on that. And then we want to have APIs and so on that are open and that lets you use the best in class algorithms for each thing. And we found that we can often differentiate from the cloud vendors on the quality of that service and the ease of use of that. So, and that's the thing we have to be really good at to win in this space. Okay. So what are the specific challenges we have? So all the usual challenges of SaaS, but also the workloads that we're running at large scale. So it's very easy for someone to run a job that makes lots of API calls to our control services. And you know, that might cause the services to crash. And also just because we run lots of VMs, we naturally see a bunch of weird things. Okay. So I'm going to talk about 4 kind of lessons or takeaways from what we saw. First of all, what are the actual causes of outages? How do we test for scalability and stability, which are 2 of the hard things to do? How to build control planes, and then finally evolving big data systems like Apache Spark, for example, to work better in the cloud, which is also something there's not that much research on, but it makes a huge difference. So let me start with this one. So there's obviously a ton of academic research on fault tolerance and reliability and stuff, verification, and it studies many kinds of failures. And, you know, it's actually done a great job of catching a lot of them, software bugs, network configuration, and so on. And these are important, but we also see lots of other problems that often have larger or more serious impact. And these are much less studied in research. So things like scaling and resource limits, workload isolation, and one I mentioned about how to reliably do upgrades and prevent regressions. So just to give you a sense of these, this is graph that our engineering team put together with the causes of significant outages in as basically the last 3 months of 2019. And so significant outages are ones where production jobs from multiple customers are affected. Sometimes I think we also consider one customer, but that's basically where like production jobs can't run. So this is the kind of thing where like you really have to fix it. It's not like, oh, there's a small bug when I click this box in the UI. It's like, my jobs are not working correctly. And if you look at this, there's various causes of problems in here, but definitely the biggest 70% of these big outages are somehow related to scale. So it's either that our services are not scaling correctly in front of the load, could be a problem in underlying services that we rely on where we have to work with the cloud vendor to fix that problem. It could also be insufficient user isolation. So some user or some tenant is stressing the system in some way that actually impacts the workload of others. So these are actually 70% of the stuff. And then there's misconfiguration and various other causes that were issues. So you can see, and these are things that like just if you verify your software or whatever using traditional tools, it's not going to find anything wrong with it. At least it's not something that people look at very heavily. So these are some examples of issues that we experience that fall mostly into this category. So one example of a cloud service issue is cloud networks. So things like rate limits, partitions, slow DHCP, hung connections. And interestingly, because these are virtual networks, they can fail in all kinds of ways that your traditional data center network where you just wired up some boxes would not fail. So you can have, some of the traffic going through, but not others. You can have all kinds of weird behaviors. I'll talk about some of them. Automated apps creating large loads. So we have an API, the user decides to call it in every function or in every record in their big data set, and suddenly there are like millions of these requests coming in per second. Very large requests or results. So, someone tries to display a record in their database, except the record is like multiple gigabytes in size. That kind of thing, if you assume that they won't be too big, it'll cause problems. Slow VM launches and shutdowns, lack of VM capacity, and data corruption writing to cloud storage. If you're doing lots of writes per day, you'll quickly see any kind of bugs that are introduced there, even rare ones. Just to give you an example of how these things come together, this is an example where some customers' production jobs that they schedule to run every night are aborted. So let me explain how this one happened. So using in Databricks, there's this feature where you can schedule jobs to run, every hour or every night or whatever you want. And we have this job service that's a central service that works, manages, thousands of customers in a region at the same time. And it's supposed to launch jobs on clusters and then track and monitor their status. So this is sitting here, and then it's talking through the cloud network and it's running these jobs on these machines. So that's fine. So now in one of our regions, one customer was running many jobs per second on the same cluster. Interestingly, this customer had set up basically like a Lambda so that whenever they upload a file into a bucket of storage, it will kick off a job on Databricks by calling our API. So that's like really awesome use of serverless, very cool. You just upload a file and it runs a job, except then they uploaded a million small files. So this created this large automated load sort of coming from the cloud provider directly. So that user started running many jobs per second. Now, it turns out that this virtual network in this particular cloud region had this limit of 1,000 connections per VM between the networks that the job service and the customer clusters are in. And after you reach this limit, it's a limit of, basically the virtual network infrastructure, new connections hang and you don't even get a reset packet back. So you send the SYN and they never reply. So now on this host, this Linux host, we had all these SYNs that were sent and nothing coming back to, and meanwhile, other connections, past connections we had to those nodes were working fine. So some of the traffic could get through, maybe talking to other ports, but other ones didn't. Okay. So this job service here is waiting now to launch some jobs, and this limit actually affected all connections between this VM and any customer. So it would affect other customers too, not just the one with lots of jobs. Now, after this, these jobs that are waiting to launch and these connections that are waiting to launch cause some resource contention. In particular, we had some information about the jobs sticking around in memory. So eventually, filled up a lot of memory, caused a lot of garbage collection, and it would have caused an out of memory eventually too. And because in this service, there's now lots of GC happening, some of the health checks we had to existing running jobs where we are able to talk to them over the network timed out. So we would say, hey, we are trying to talk to this job that we started, hours ago, and the health check where we ask it periodically what it's doing times out. And so we decide to abort them and we send a packet on that connection that's still working and say, please shut down this job. So this is an example of where there's all kinds of interesting scale and isolation related behavior, right? We had this very weird failure mode for the network where some past connections worked fine, but new ones did not. It actually caused different resources to get filled up that caused an assumption about timing to break at the end, where we thought that, if we waited a minute on a reply, maybe that thing went down, but actually that 1 minute could have just been spent garbage collecting or something like that. So that's an example. There are also some pretty rare issues that we saw. So in the whole lifetime of the company, for example, we just saw one case on AWS where the cloud provider said we have to restart all your VMs, which was dispatched to Zen a few years ago. We had one example of a misreported security scan. So this customer had some kind of product that checks whether their VMs have a virus or have been compromised. And they got a message saying your Databricks VMs have, malware on them. And of course they freaked out. They said, can we shut it all down? How did this happen? What's going on? So that's where you have to do an investigation of everything to see what was it? Was it a false alert? We had one significant S3 outage that caused these kind of, very notable issues for customers. And we had one kernel bug, which was interestingly also about networking, where some connections would hang in a weird state. There might have been like one more kernel bug recently that's an issue. But these issues, people are doing a great job of solving these issues. So we haven't seen that many of them. Okay, so the interesting lesson is that cloud services have to handle load that varies on many different dimensions, and they also increasingly rely on other services. As you saw, we rely on the cloud providers, and of course, our customers rely on us and on other things as well. And these have very different limits and failure modes. And some of these particular situations, even if you've got a lot of customers and like millions of jobs running, you might only see them once every few months. So this is something that's pretty hard to reason about, and it's likely to get worse as more and more applications start building on these services and interacting with each other this way. So that's one that's one takeaway about what's failing. What like really bothers us is usually this kind of stuff. It's not like there's a null pointer exception in this code or something of that form. Okay, so this leads me to the next point, which is about testing for scalability and stability. So as I mentioned, these are significant cause of outages. So what do we do to test for them? So it turns out it's kind of hard because there are all these factors. So this is actually something I worked on earlier on in the company. It's a small piece of the talk that I actually directly worked on. So let me talk about how we were thinking about that. So when you think about testing for correctness, correctness is a Boolean property. Does your software give the right answer given an input or not? And so you can figure out there's all kinds of strategies, but that's basically what it is. Now, how do you test that something is scalable or is stable? So these properties are actually a matter of degree. There's no just Boolean like, yes, this thing is scalable or it isn't. And it's really kind of two questions. So there's what load will the system fail at? So any system with limited resources will eventually fail at some load. So the question is just how much. That's one of the questions you have to answer. And you don't want this to be going down over time. And then the second one is how does it fail? You know, when that load is reached, what happens? Does it crash all the clients? Does it drop just new clients? You know, what happens in there? So as you saw in the example I gave before, the system, because one client was putting a high load, it actually messed up existing jobs that were happily running. So that's an example of a bad failure behavior. So you want to aim for good behaviors. So I'll just give you some example problems that would happen. And these are some of the ones that happen very early on in just the basic Databricks sort of interactive data exploration service, which gives you, you know, a notebook in your web browser to run computations on Spark or on, you know, on whatever you have on your distributed cluster. So this seems like, you know, it's a pretty straightforward product to do. Just take something like Jupyter, you know, stick it in front of a Spark cluster, you know, and go at it. How hard can it be? Like what can go wrong? But it turns out there are a lot of interesting problems even in this setting. So what we've got is you've got a user, you know, they're going, you know, they're using their browser, they're talking to the service, and then on the cluster, we have this driver application, and then a Spark cluster and some workers. It turns out pretty much all of these components in here could have some problems, and we experience problems in all of them. So one example of a problem is if you have a large result from one of your computations. So imagine, you know, you're getting records from a table, or you're computing a machine learning model and trying to display it, whatever it is you're trying to do. So this could crash. It could crash the Spark workers or the Spark driver as it's sending the data back. It could actually crash this app that we put in front of it, depending what you're doing with the result. It could cause problems in this notebook service. If, for example, a lot of people are viewing large results, it might cause, you know, the whole thing to like run out of memory or something. It could actually crash people's web browsers. We had that happen as well. And so at all points in this process, you have to deal with, you know, what happens in this particular scaling dimension if you've got a large result. Another example is a large record in a file. So like anything you write, you know, you're clever with how you're doing the data processing. There will be some user among the millions of, you know, potential users and all the data sets they read who'll have something weird. So they'll have the table with 1 million records or whatever, or with 1 million fields or whatever they've got. And so all these components have to deal with that. Large number of tasks in a job. Now you're trying to display and schedule these tasks, or code that crashes one of the workers. So imagine you submit some code that causes one of these to, you know, to just crash. Now it affects everyone who's running on that Spark cluster potentially. And you want to make sure that they gratefully, you know, recover from that. And so, you know, all of these also affect any other users who are sharing the cluster. And it's important for users to share a cluster for cost efficiency and elasticity. So these are, you know, just some example problems. So how do we test for them? So we actually built this test infrastructure that works in the following way. So first of all, it's all focused on scaling dimensions. So we identify dimensions that a system should scale in. For example, number of users, number of output rows in a result, size of each output row, you know, in bytes, latency of an RPC. For example, when we're talking to the cloud service requesting VMs and it's taking 20 minutes to spin up a VM, these are all scaling dimensions. So next, we grow the load in each dimension until some kind of failure happens. So interestingly, we just look at each dimension by itself. We found that this actually captures most types of failures. Like if there's something that's going to break, you can exercise it just by pushing one dimension at a time. And that avoids the combinatorial, you know, explosion of lots of them. Next, we record the failure and the impact on the system. So for example, did we see an error message? Did it just hang? Did we get the wrong result back? And also what happened to other clients who are connected to the system at the same time? And finally, does it auto recover, or is it just borked and you have to go in and do something, call someone to fix it, or press a button to restart it? And how fast does it recover? So these get to that question I asked about failure behavior. You are going to fail sometimes, but what happens in that case? How do you make it better? And then finally, we compare this over time and whenever we have a change to the software. So this is how it worked. And this here is an example of the output that it gave. So this is a really old example that's in a Google sheet. But basically, you see we had a whole bunch of tests in here. For example, this is if you're using Scala on a cluster. These are the different dimensions we want to scale in. So for example, we're broadcasting something large. We have lots of tasks. We're caching lots of objects. We're displaying large rows, whatever it is. And for each test, we record the max value that we were able to scale to, what happened after. So failed, for example, means that you got an error message, which is actually a good outcome because we actually told you something is wrong and why it's wrong and how to fix it. Timed out is worse. How many steps it went to. And we also compare to the previous value and the previous state. And you can see in this right column, you can see, okay, some things got better and some things got worse over time between these two runs of the software. So this is kind of the approach we took. There's more refined versions of this, for various use cases now, but it really helped nail down these problems from where it went to like each week there are, many new and previously unseen kinds of problems to having, a few tests that push each of the dimensions and they actually catch 99% of what's happening, even as the number of users and the scale of the workload is increasing. So this is one example of a thing that we learned. Okay, so that's scalability and stability. So next, I want to talk a little bit about developing control planes, or these shared services that have many users going through them, and some of the stuff we learned there. So it's not just about scalability, it's also about just how to build them. Finally, I'll talk about the big data systems too. So cloud software, as I said, consists of these interacting, independently updated services, and they just end up calling each other all the time. And so the natural question is, what is the right programming model for this kind of software? And it's pretty different, again, from anything you might have built as a package software, or even anything you might build as like a consumer-facing, say, web application or mobile app. If we're talking about an enterprise system where there are many services interacting, so that's the question. We spend a lot of our time building these. So just as there's obviously a lot of work in this general area on microservices and actors and all kinds of stuff. So just to give you a sense of some services at Databricks, we've got something called the Cluster Manager Service, which launches and scales and shuts down clusters in each customer's account. And its job is to request the VMs, talk to the cloud provider, set them up, and also reuse VMs across workloads. If the user is shutting down a cluster and launching a new one, we can reuse it to save time and cost. And then it's also managing some state, like all the requests that someone sent it that it still has to fulfill, and which VMs are running, and so on. Another example of a service is the job service I mentioned. One of the things that clusters can do is run jobs. They can also run notebooks or other stuff that is not jobs. And so this thing, the API here is you schedule or you trigger jobs, and it talks to the cluster manager to acquire a cluster, and it tries to monitor its state and to retry it, if the job fails. And the state is, which jobs you have to run, what's active, which cluster is it on, and so on. So this is an example where these two things have a dependency, and actually, different engineering teams that are building these, they're releasing them and upgrading them on a different schedule. And so you need to figure out how these teams are going to build these things and interact between them. And these also talk to many other services. So some of them are things we support, such as, billing, pretty important to actually figure out how many compute hours they use and bill them for them, or notebook service. Some of them also talk to external things like the cloud VMs, that we request from the cloud provider. Okay. So to build these services, we and pretty much everyone else in the space usually design some kind of software stack or service framework for it. And so as an engineer, when an engineer comes in, they get a lot of standard features around their service kind of for free if they work within this. The service framework handles deployment. For example, how do we deploy the same service in Amazon and Azure and local environments? Storage, what maintains a database for it or whatever other storage it needs, security tokens and roles, monitoring, API routing, rate limiting, and also flags to incrementally deploy and hold back features. So we built our service stack using these open source components out there. But I think this is one example of a question where, you can talk to people who are doing these and figure out what's needed in this and how to make it easier to build these, because it's a lot of work to maintain this. So what did we learn in building these services? So the first one is, you want to take care that the state is okay, and make sure that it doesn't get messed up. And in pretty much all our services, we just use relational databases and we shard them by customer, and it works fine. And that's the simplest thing. There's a lot of expertise on how to do it, so we just do it. Don't try to get fancy here. Make it super easy to understand and to manage. The second thing is to isolate the components that scale differently. So this is sort of non-obvious, but I'll show an example of this later. But basically, if you've got, your application has to do several different jobs, and they might get varying loads at different times, it makes a lot of sense to isolate them this way and to make sure that if load in one API, for example, goes up, it doesn't break all the other APIs. So this minimizes the sort of the blast radius of a failure there. The next example is to manage changes through feature flags. So we tried lots of ways. We said, what if you can just roll back really quickly? What if some features are super simple and you don't need a flag? But basically having a config flag that you can flip ideally while the service is running to change something is the fastest and safest way. So everything new we do, even though we might think we'll never roll it back, has a feature flag. Next thing is, how do you monitor these? So I talked about all kinds of complicated, metrics that might be happening, like, for example, what % of connections are failing, between us and the customer VPN or stuff like that, or, how many jobs are in the queue. But it turns out that actually most outages that we had could be predicted by just monitoring standard system load metrics. So CPU load, memory load, load on the database, usually CPU load as well, and thread pool exhaustion. So it turns out if you just watch these, you could actually catch most of the outages and scaling regressions that we had. So kind of an interesting finding that you don't necessarily need more than this, but you do need to actually watch these and quickly detect what's changing. And then the final thing is testing, and sort of the standard test pyramid that has both unit tests and end-to-end tests helps a lot. If you can't test your cross service behavior in a unit test, you're gonna be in for a lot of trouble. So you need to figure out how to make it unit testable. So just as an example of the second point I mentioned about handling load, this is a similar one to the one I had with the jobs outage. This is an example of how we improve the stability of our cluster manager. So initially, the cluster manager was a set of VMs. Basically, there are several instances of it, but the same instance receives the requests about what clusters to launch and stores them in the database, and it also talks to the cloud API to actually launch the clusters and then to configure them and kickstart our processes on them. So it seems pretty simple, but it turns out that a lot of failures were caused between this cloud API and cluster manager interaction, where various things can slow down or whatever, or there are limits. When those things break down, this whole thing was unable to accept requests from outside. So instead, we split it into these two sets of services that scale independently. So there's the master, which receives the requests and record them and manages billing. And then there are these delegates that do the heavy tasks of talking to the cloud vendor, launching a cluster, setting it up and monitoring it and so on. And this means that if some of these are failing, it only affects a few clusters at a time. And also we never lose the request to launch clusters, and we get back and actually do them eventually. So that's an example of this isolation and kind of putting the scary stuff that we can't control in a box where when it breaks, it doesn't mess up too much stuff at once. Okay. So that's a little bit about control planes. There are a lot of interesting kind of open questions there. For example, how do you implement these architectural evolutions without breaking stuff is an interesting one. We have to have a big design doc each time it happens. So you could imagine, what's a programming model that lets you do these? And there's also like, how do you automatically decide the right components to isolate and so on? So these are some example questions. Okay, and then the final thing I'll briefly talk about is evolving big data systems for the cloud. I don't know, I'll try to just give a very quick overview of this to have some time for questions, but we also started a little bit later. So, basically, there's a big opportunity here to kind of rethink most types of software, including these big data systems, for this highly elastic, cloud environment. So things like MapReduce and even Spark were primarily designed for on-premise data centers. And if you are going to be in this cloud environment with many tenants and elasticity and so on, there's quite a bit you may want to do differently. So in Databricks, we have a lot of examples of that. We actually have a whole bunch of work on Apache Spark on having a proprietary scheduler for it that can do autoscaling and having much better connectors with cloud infrastructure and dealing well with spot instances and so on. And we also have this new storage management system, Delta Lake, that gives you a very, much better abstraction for managing storage, tabular storage, over cloud object stores like S3, and it's sort of a cloud native design for that. And so that's the one that I'll talk about the most here. But both of these are things that kind of embrace the cloud and design the system directly for it. So just a very brief overview of Delta Lake. So the motivation is that all our customers want to store stuff in these object stores like S3, Azure Blob Storage, because they're extremely inexpensive and extremely highly available. They have high parallel IO bandwidth. So they're just basically the ideal, kind of storage system for long-term storage. But the open source big data stack was designed for this on-premise world where you're managing lots of different services and they have much stronger consistency guarantees than the cloud object store. So for example, file system APIs, Hive and systems like that assume that you're also willing to run your own relational database for metadata. A lot of systems assume you have Zookeeper as well. So these are things that our customers don't necessarily have, and they don't want to have them. The whole point of the cloud was that you just focus on your workload. You don't have a big ops team that's running this kind of stuff. So the question is, how can big data systems fully leverage cloud object stores? And the basic idea of Delta Lake, if I were to say it in one kind of sentence, is Delta Lake is kind of a bolt-on consistency type system that gives you serializable ACID transactions for managing tables over cloud object stores. So it lets you store these tabular data sets and do ACID transactions on them, and it manages the log. Basically, the only dependencies it has is on the cloud object store service itself. So you don't need to run any of this other stuff. And it actually gives you, higher performance than the Hadoop data stack running in the cloud using this very simple design. So I'm going to skip some of the details on you know, what you needed and so on. But basically the idea is, you know, is we have a transaction log within the object store itself, and that leads us to these, you know, these significant benefits. So this is an example of a system. You can read more about it online. I don't have a lot of time to talk about the details, but this is one thing that actually had a huge impact on usability of Databricks. Before this, about half of our support tickets that we got were about consistency issues with cloud object storage, essentially, and they all went away. So it's, you know, it definitely had a big impact this way. And you can read, there are some example use cases of very large scale use, such as this Apple use case that they talked about at Spark Summit. Okay, so yeah, just to conclude, a main message I have here is the cloud is really the way that software is being delivered now, and it's understudied and it's kind of hard to build them. And there's this big opportunity if you are, you know, a systems researcher, like what's happening in computer systems. This is the majority of computer systems today. So you'd better, I think, you know, kind of begin to understand what's happening there. And there are a lot of opportunities to build these. I'm happy to talk more about them. And at Databricks, as people probably know, we also have a lot of, you know, research internships and lots of opportunities to collaborate on some of these problems as well. So that's it. I'm happy to answer any questions. However you guys want to do it. If you don't want to unmute stuff, you can also use the chat or whatever works for you.
So I was actually thinking, let me go ahead and unmute it for now if you run into any problems. Now you should be able to unmute yourself and ask any questions if you have any, sir.
Hi, this is Lan from VMware. Yeah. Thanks, Matei, for a very nice talk. I have a couple of questions. First, like I see that like this Databricks service is deployed on Azure and Amazon. Is it this multiple cloud is for the reason of data locality so that customer can integrate with their existing application on those clouds?
Yeah, absolutely. So people have data and applications on each cloud already, and they want the compute to be near the data. So you have to be wherever they are. So yeah, and we started with Amazon and Azure because they were the biggest ones. Yeah.
So is that then they plan to like expand to Google Cloud as well?
We definitely like to extend to other cloud providers. Yeah. So I think over time we'll do that.
Yeah. It's very cool. And I have another question. It's one of the slides you mentioned that like with like more than 1,000 employees, then the number of engineers is 200. Mm-hmm. Is it the ratio is about 1:6 or so? So is it the same ratio that you maintained from the day that Databricks started like 7 years ago, or it changed over time?
It changed over time because as you have customers, well, and also as you have a product, you need to hire a sales force and you know, customer success group. Yeah. By the way, these engineers are just the ones working on product. There are also, you know, like solution engineers who work with the customers. I'm not counting those in this.
Okay. Yeah. Yeah. Cool. Thanks.
Okay. I see a question in from Iman about Kubernetes, whether we're using a custom scheduler for Kubernetes. I think we're just using the default one. We don't have that many you know, pods and stuff in our control plane really. So I don't think we've had to do anything super special there. But the Kubernetes is just for our control plane services. It's not for running the Spark clusters themselves. That's what our cluster manager does. That's a different thing. And that's really integrated with Spark. Yeah.
So Matei, here is Jon, and very nice talk. And you know, so I'm just curious, you know, like you mentioned a few things, and of course I'm very familiar with some of these things, about insights, so to speak, over the evolution of during, you know, the growth of the Databricks. I think one thing is that, you know, if you have components which have different scaling behavior, you better isolate them. Then obviously you said about, you know, mentioned about the Delta, which removes and make it much easier to use for people. any other things you think back, you'd like to single out as being some more inflection points, which, you know, in retrospect, maybe even could have been obvious, but, you know, you look back and say, well, you know, this was one thing which also, you know, contribute a lot at both scaling and robustness. And I know that you put a lot of things here. You have a lot of things in your presentation, but just I'm asking a little bit of more ranking them.
Yeah, actually, let me see. Can you still see my screen? You can, right?
Yeah.
So there is one thing. I don't know if this is an inflection point, but definitely. So where do I show this? So initially, this I missed it. So it's about the shared control plane. So this thing, as I said, this is actually a set of VMs and stuff that are shared across many customers. So actually, in our first version, we had a different instance of the control plane for each customer, which was, you know, it was easier for them to approve it from a security standpoint, and, you know, and so on. And when you only have like 5 or 6 customers, it's okay. But then moving to this was a big challenge. But and once we moved to it, though, and we actually had all that figured out, it made it much easier to do operations. So when we had separate instances of the control plane per customer, that for a while became a bottleneck. I would also say that just being able to use your product itself is also an inflection point. Like when we were using it ourselves, it got a lot better. So
Yeah.
that's a big thing. Yeah.
Yep.
But yeah, this is one, because sometimes people ask like, can't I just start by, you know, just having a separate instance for everyone? And it's okay at the very beginning, but then it actually, like, you know, it becomes a problem later. Yeah.
Matei, is Justin here from VMware. I was curious, you have 2 workloads, data analytics and machine learning. I'm interested in whether they stress the system in different ways. Well, I know that machine learning probably uses GPUs, but do you see different stresses coming from those different application types?
From data analytics and machine learning, I think at a high level they are pretty similar, but there are definitely different use cases. So for example, the data analytics ones have a lot more concurrent users. So data scientists or analysts making concurrent queries, you want to have, you know, hundreds of people connected to the same cluster who can spin up a query. Machine learning, there are just fewer individual people using it, so you don't have to worry as much about concurrency. I would say that's one. For machine learning, we're not currently doing model serving, but I think with model serving, that will also have different requirements. Although some of the stuff we're doing, like just our existing APIs to run a SQL command or even a Python command, are used in, you know, in kind of real-time applications. So those have a, you know, when those started, that also created a shift where, like, you know, it's not okay for this thing to be down for like, you know, a few minutes or whatever, even while we're upgrading other services.
Thank you. Great answer.
Yeah.
Just a follow-up though. In the ML space, do you see people asking for multiple GPUs for their jobs or just one or partial?
Oh, yeah, good question. So it depends a lot. I think multiple machines is definitely not common, but one machine with many GPUs is pretty common. But my view of this is, you know, most people who use ML, they want to pick a model that's designed by someone else, and ideally the code's been written by someone else and it's high quality, and they just want to run it on their data. So it depends also on what's available. So if you can, for example, with something like TensorFlow, it's easy to find a multi-GPU but single machine example. It's harder to find a distributed example that like really works and, you know, actually performs better and so on. So people will pick the easiest one.
Got it. Thank you.
Yeah.
Hey, Matei, this is Malhar. So regarding when you discuss stress testing infrastructure, especially when you're dealing with thousands of different customers and how scaling up to that many VMs could cause certain issues, how do you go about internally replicating those issues without necessarily having to spin up the same amount of clusters?
Yeah. So that's one of the things that was surprising and interesting in the scale testing stuff is, it sounds like and a lot of engineers also who come in say, whoa, we need to create an environment that's exactly the same distribution of data, of job sizes, of number of users, like whatever, and that's going to be really hard and really expensive. But in fact, what we found is when something tips over, it's because some resource got exhausted, and there's usually just one scaling dimension you can test on that will exhaust that resource. So just by pushing in each dimension independently, you actually catch all the things that can get exhausted and all the failure behaviors there, so you can improve them. You can go from hanging or crashing everyone to just failing that one user and giving them a nice message. And then your thing actually becomes stable to whatever weird stuff is happening in the real system. So that's one surprising thing I took away from it. Of course, the better you can do to replicate real workloads and so on, the safer you'll feel. You can also roll back stuff incrementally and check that it's okay. Maybe check those CPU and memory metrics before you push it out to more users. There's various ways to do that. But even if you could perfectly replicate today's workload, the problem is it's going to change, right? A week or two from now, it will be bigger. Someone will onboard and do some crazy thing they've never done before. So I don't think with a workload that's changing, you can't just say, I'm going to replicate that and test on it. You have to expect these new failures or these new unanticipated things. Yeah.
Hey, Matei, I have an additional question. Like from a diagram architecture, I saw that like the customer data mainly on Amazon and Azure. It means like Databricks doesn't host data by itself, right?
Yeah, it's
so
in
it
their
more
account.
provide an interface.
Yeah, exactly. We just access, so the clouds all have this IAM permission. So we can get a role where we're allowed to access just the data that they want our jobs to get. And it's also very easy for them, they maintain control over it. And if they decide not to use Databricks, they can easily shut it down and they don't even have to migrate data out of it. So we think this is kind of the most customer friendly approach. And as I mentioned, there's also a financial thing. Like we could say, wow, we're going to charge them like $1 million to store their data, and that's $1 million in revenue. But then it's also $1 million we have to pay to Amazon. And it means if the customer, doesn't pay us, we're at risk where we have to pay Amazon and we're not collecting stuff. And it's also bad in terms of, investors don't like that too much either. It's a company that's like, seems to have high revenue, but it's really like low margin and incurring all this risk in the future as it goes. So that's why we did it that way. Yeah.
So in that case, it's like at some point, the Databricks want to offer and like same service, but the data is on-prem from customer.
It's possible, yeah. It's just a question of so many people do connect to on-prem data already. Actually, we don't really care where it is. Yeah. So it's definitely doable. Yeah.
So it basically an API or an interface that customer can inject to their data center, right?
Yeah. Yeah.
Okay,
yeah.
got it. Yep. Thanks.
Okay, cool. I see one question in the chat. Do we use spot instances and how do we navigate the cost availability trade-off? So we definitely do. And more importantly, we let customers pick to use spot instances. And people have different needs there, but basically, for many people, just bidding at the same price as the on-demand instance is pretty good for most scenarios if they want their job to end at a predictable time. There are also some people who are okay delaying their workload and they'll do something, fancier. They'll retry the job a few hours later. We don't have it's so specific to each use case that we haven't tried to give you like something that automatically sets your spot bid or whatever. But we do make sure that you can use them and you can also fall back to on demand if the spot ones are not available. Cool. Okay. I don't want to keep people too long necessarily. But yeah, let me know if you guys want to take more questions or not.
Yeah, it is already 10 past and maybe you have other meetings to get to as well. So.
Cool. Okay.
Yeah, I'm not sure if we can applaud here, but thanks for the talk, Matei, and we appreciate you.
All right. Thanks for having me. Yeah. Yeah. Take care.